Hello, Calc 3 students. So in this video, I want to recap everything that we've done so far because this chapter is a little gnarly and it has a lot of different convoluted topics. So it's really easy to kind of just mess them up. So the first thing that we talked about was line integrals over scalar fields. So here, a line integral, if I kind of want to give you an example or a picture of what this looks like, you essentially have this surface f of x comma y. Doesn't necessarily have to look like this, but just for the sake of this section, I just want to show you. So you have f of x comma y. You have this curve that you parametrized on the xy plane, okay? And it can also be on the xz plane or yz plane, but I think this makes it a little nicer to see. So you can all you just really are doing is finding the area underneath this little curve. Okay, so it's just an extension of the fundamental theorem of calculus, part 2. But instead of integrating over a line segment, you're integrating over this curve C. You can also extend this to 3 variables, x, y, z. And the formulas are just exactly the same. You just have this extra z component. Now, remember that the parametrization itself, there's a little mistake here. This should say A to B. A to B, so just give that correction. So remember that this parametrization has to be done on the curve C. So you need to be able to parameterize this curve. Sometimes the parametrization will be given to you, sometimes they will not. So if I give you a line segment, if I give you like a circle or just a general function, you need to be able to parameterize curves that way really easily. One thing that I will say is that typically, especially for this integral, the parametrization is given to you. So parametrization is usually given for this one. And it's typically written as like R of t is equal to whatever x of t is, whatever y of t is, and whatever z of t is. Okay, so they can give it to you in component form, or they can also give it to you in IJK form. So either or, sometimes it can also be given to you in the first type of integral as well. So it really just depends. So that was the line integrals over scalar fields. So we have functions, no vector fields at all. Okay, now what we're doing, we have a line integral over a vector field. So what's happening there is that you have this xy vector field. So you have like maybe like a current or wind or I don't know, something's going on, magnetism, electricity, something's going on here. And you have all of these vectors that are doing weird things. Okay, so you have this vector field, and what you want to do, you basically have a path. So maybe this particle, it could be you, that are taking a path, and you're going from school to home in a orientation, in a particular order. Okay, and what's happening is that you want to be able to calculate the work done. So you can think of this guy as the total amount of work that's necessary for me to go from point A all the way to point B. So here the orientation in which you travel will matter. Okay, so the way to do that, same thing, you have your vector field and you're going to take the dot product with dr. And dr in this case, we proved it in class, is just going to be r prime of t dt. So you have to take the derivative of our rt. Remember, r of t is the parametrization. So parametric equations. Again, this can be in xyz or in just xy. So if I were to kind of extend this idea to 3D, you can obviously have a vector field in 3 dimensions. So going kind of outward. So maybe you had this source. So going in the outward direction or something. So if you have this vector field and you still have a curve in 3D, okay, you have this parametric curve and this path, then what you can do is you can still calculate the work in space. Okay. Again, remember it requires parameterization. Sometimes it will be given to you or sometimes it will not. So again, with 3D, it's a little harder to parameterize. So it usually will be given to you. When you have something like this, you can parameterize it pretty easily. Okay. So these two are kind of like the long ways to do it. So this, or at least number 2 is the long way to do it. Then you have a couple of specialties. So you're still finding the work, but now you're doing the fundamental theorem of line integrals. And basically what that says is that if you know that your vector field is conservative, okay? So for example, if you have a function or a vector field that has P and Q as components, and then you know that this guy is going to be conservative, as partial P over partial Y equals partial Q over partial X. So if this is satisfied, then you know that this vector field is going to be conservative. Another way to think about it is that if you have 3 components, P, Q, and R, then a really easy way to do this one is to find the curl. So if the curl of F is equal to 0, then in that case, it's also going to be conservative. So this is kind of 2 ways that you can check it. So if I know that this guy is conservative, then you can find a potential functions, just how we did in class. So you can find this potential function f. Okay, so you need to figure out what f did this vector field originate from. And you're going to have to plug in the endpoint. So this is kind of like the end point, and then this is going to be the initial point of where you start, like the end minus the starting point. The good thing about this is that you may need to parameterize the curve. You may need to. You may not need to. All you really need is the endpoints. Okay? Because all you got to do is just plug them in and just get your answer. So if you wanted to find the work, so same thing as number 2, but in this case you have something that's conservative, then you can just use the fundamental theorem of line integrals. Okay? Now, the fourth thing is Green's theorem. So we're still finding work. Okay, we're still finding the total work. The only thing about Green's theorem is that it's probably the easiest case in the sense that you don't need to parameterize because you're dealing now with a double integral. So you want to use Green's theorem when doing a double integral. It's easier for you. Now you have certain requirements. In order for you to use Green's theorem, you require the curve itself to be closed and counterclockwise. So if you want to find the work over a vector field, you would require the circle or whatever this may be over this vector field to be counterclockwise, and it has to be closed. Okay, so you would have to do something like that. So instead of doing the parametric equations over this little thing, all you got to do is just integrate over the region D, over this circle, which will involve converting to polar and all that really good stuff. So this one, it doesn't need to be conservative. So you don't require the vector field to be conservative. You can certainly check. But this one does not need to be conservative, okay? And you want to do it when one double integral is a lot easier for you than the other, okay? So this one is a really good way to kind of just be able to find the work, but you require it to be close and counterclockwise. All right, so this was vector fields and scalar fields. Now the last thing is surface integrals. So in the next couple of videos, I will be doing a whole bunch of examples of these, so that you can get a little bit comfortable. But pretty much what's going on with surface integrals is that now it's a little bit different. So now what's happening, and I'll give you kind of an example of what really is happening with the surface integrals. You typically have this surface, kind of like the same scenario. You have this surface. And I think the best way to kind of think about the surface integrals over scalar fields, it's imagine that this guy right here, this f of x comma y comma z, okay, or I can call it this guy. So this guy, imagine that it's its density, okay? So at every single point of this surface, so a point here, a point here, a point here, a point here, has different density. So maybe it's really dense over here. Maybe not as dense over here, maybe a little bit. And then more dense in here, and then more dense in here. You know, so it's really dense. So you have like this surface, this little plate, that doesn't necessarily have to be thin. It's now more whole, and it's dense in certain areas. And what this surface integral really is doing is finding the mass of this guy. So how much mass does this guy have given this density? And you're multiplying it by the surface area. That's where this ds means. It's the surface area of each little patch of surface. So use these formulas, these three different formulas, when you have a basic parametrization. So if you have a really basic where z is in terms of x and y, something like this, or y is in terms of g of x and z, or x is in terms of y and z, use these guys. Here are the different formulas to use. So you do need to parameterize your surface itself. Again, those worksheets are available to you on the notes. So if you want to find something like this over scalar fields, you do need to do a parameterization of these functions. Luckily, they're really easy to do. This is typically your parameterization, and just plug everything in there. And the integral typically is kind of not that great. If you have a different parameterization, so for example, you have like a sphere, or you have a cylinder, where you have to convert to spherical or cylindrical coordinates. Well, in order to find the surface area of this thing, what's happening here is that you're going to take the cross product of the parameterization by the two different variables, and take the magnitude of that. Okay. Think about this as kind of like finding the area of a parallelogram using two vectors. So that's kind of what's happening here. So you're doing the same thing, but now you have a different parameterization, like a sphere or a cylinder. Okay, something that's not as basic. And the last thing is just the surface integrals over vector fields. So again, what's happening here is that you have a surface integral, okay, and you still have the same format. You got this surface going on. The surface. And now what's happening is that we're putting the surface now on a vector field. So you got this vector field that's acting on it. So it can be anywhere, I don't know. So in order for me to be able to do this, well, now it's a little bit different, because now we're not calculating work. What we're really calculating is flux. So the amount of flux that is going through this surface. In the positive orientation. So if you have a basic parameterization like z equals f of x comma y over some vector field f that has components p, q, and r. Oh, let me change this f to g. That might be a little easier to work with. So if you have this guy, then all you're really going to do is take the partials with x and y, multiply by the negative of p and q, and then add it to r. So that's how you would find the flux over a basic parameterization. If it's not basic, if it's like a cylinder or something else, then you're going to do this other thing to find the flux. Instead, you're going to still take the dot product. This essentially is a dot product, but it's over RU cross RV. So notice the similarities between the vector fields with the scalar fields. There's a lot of similarities in here. Okay. So you got that guy. And now here is kind of like the easiest way to do it. Again, part 6 is kind of crazy. Part 7, the divergence theorem. What's happening here is that now you have a closed surface. So I'm just going to say that this guy is closed. So this guy, imagine that this surface itself is closed, okay? And you're trying to figure out the flux, the flux over this guy, okay, over this vector field. Well, if I know that it's closed, if I know that, then I can use the divergence theorem, which basically says that instead of doing all of this complicated stuff with messy integration and a whole bunch of cross products, all I can just do is take the divergence of f. Remember, the divergence of f is just a sum of all the partial derivatives. So partial p over partial x plus partial q over partial y plus partial r over partial z. So I can just take the sum of each individual component, differentiate it with x, y, and z, and then add them all up and get the divergence. And now you want to do this triple integral. And typically this triple integral will be a lot easier than working with something that's really crazy over here. So this would be the divergence theorem, requires no parameterization. So imagine kind of like it's very similar to Green's theorem. Okay, kind of they're kind of analogous. So we're going to be doing a lot of problems with these types of integrals. Now there is one more theorem, which is called Stokes Theorem, which is just an extension of Green's theorem, and that will be in another video. You're basically now relating line integrals with surface integrals, and you can kind of see the Green's theorem. If you compare this with Green's theorem, you can see the similarities. Okay, so this video, sorry, is way too long now. It's for a recap, but hopefully this helps you kind of realize what exactly is happening in this particular chapter. Okay.